Okay, so today we'll talk about the second law of thermodynamics. Okay. So the zeroth law says two objects in contact, they're at the same temperature if there is no net exchange of heat. The first law of thermodynamics is a conservation of energy principle with heat included. What does that mean, conservation of energy?
The system stays constant.
Yeah, so if you have an isolated system, okay, no matter what happens, the total energy of the system is constant. So if anything is happening, energy is just moving around. All right? In fact, from an energy perspective, everything we do in life just amounts to moving energy from one object to another, or converting it from one form to another. So this is the conservation of energy principle. When do you need a new law?
When things are no longer able to be explained or don't follow these rules.
Yes, so if you come up across a phenomenon when the existing laws cannot explain it, then you need a new law. All right, so let me give you an example. So here's a room. And here's a hot cup of coffee. Okay. If I let this coffee sit, what will happen?
Thermal equilibrium.
Yep, so the coffee will get cold, so I'd better drink it fast. Yep. The room is large, so all right, we'll just say 21 degrees. All right, so what happened?
They reached thermal equilibrium as the coffee gave off heat to its surroundings, and the surroundings absorbed the heat from the coffee until their net transfer equaled zero.
So all that happened was a bunch of energy moved from here to the room. All right, why doesn't this happen? Why can't you move energy from the room to the coffee cup, and I bring a cold cup of coffee, and by the end of my lecture, I have a hot cup of coffee?
You can.
Huh?
Can you not?
This never happens on its own in nature.
Oh, if the room isn't hot enough.
What's that?
If the room isn't hot enough.
No. I want from a cold room for heat to flow from this room into my cup and warm my coffee.
Because heat always flows from hot to cold. It gives
Okay.
more energy to
Oh,
the
because
center.
it's spreading.
Yeah, because
It's not
the universe
focusing,
wants
it's
to be
spelling.
random.
All right, so the point is the following. So, I mean, it's such a thing that you live with that you don't even think about it. Well, the existing laws cannot explain that fact. The existing laws can't tell you why heat wouldn't move from the cold room and warm my coffee. Okay. We're all saying heat flows from the hot region to a colder region. Why is the question? Why doesn't heat flow from a colder region to a hotter region? That's the question we want to answer. Okay? And that's what the second law of thermodynamics says. Okay? So you just come up with a new law saying, okay, it doesn't happen. This never happened. Okay, so we'll put some quantitative numbers to it. Okay? So I'm going to give you the punchline, and then we'll go into the slides. Okay? Okay, so let's say this end of the table is hot and this end of the table is cold. Okay? What will happen? Heat will flow in that direction. That's what always happens in nature. This never happens. And we want to explain that. Okay? And let's just put some numbers, okay? We'll say, okay, heat flows, let's say about 50 joules of heat has flown in this direction. All right, or we'll make it 100 joules. Okay. We'll define, I'm just going to define something called delta S, and we'll give it a name in a second. Delta S is the amount of heat absorbed or given up divided by the temperature. All right, so this is some new thermodynamic variable that I'll tell you about in a second. We're defining. The change in this thermodynamic variable is the heat absorbed divided by the temperature. Okay? And this temperature is in Kelvin scale. Yeah. Okay. So let's say in this process, how much did this thermodynamic variable change? Okay. So here's your system, and for our system, we're going to calculate the change in this thermodynamic variable. Yeah. Well, this part of the system lost 100 joules. This part of the system gained 100 joules. Okay, so the change in this thermodynamic variable for the system is change for part 1 of the system plus change for part 2 of the system. All right, so if the system absorbs heat, that's positive. Remember, that's what we've been doing. And if the system gives up heat, that's negative. All right. So this part of the system gave up 100 joules minus 100 joules. And the temperature at which it gave it up is 100 degrees Celsius.
373.
Very good, my friend. You've been listening. 373 Kelvin. This part of the system gained the heat. And what is the temperature? 273. Okay, let's look at this carefully. See, this denominator is bigger and this denominator is smaller. So here's a number that is greater than 0. Okay? All right, let's defy physics laws. Let's move 100 joules in this direction. Okay? All right, let's calculate the change in the parameter in this scenario. Right. So there's part 1. In this scenario, it gained 100 joules. Okay? So change in entropy would be plus 100 joules divided by 373 and minus 100 joules divided by 273. This is less than 0. This number is bigger, absolute value, this number is bigger, and this is smaller, this is less than 0. All right, there you have it, your new law. What's the statement of your new law?
In natural systems, delta S should always be greater than 0.
There you go. See, if you had said this 300 years ago, you would be rich and famous. And that's the second law of thermodynamics. All right. So only processes where the And this fellow is called entropy. Entropy measures the disorder in the system. It tells you how much energy there is that's not available to do work. Thermodynamics was invented when we tried to convert heat to work and so on. So what is your new law? Only processes where the entropy remains constant or increases occur in nature. Okay? So in all processes, change in entropy is greater than or equal to zero. Okay, so that's the second law of thermodynamics. So this guy doesn't happen, this guy happens. All right. That's this chapter. Okay. Well, and also then we'll talk about heat engines and all that kind of stuff. But we've already talked about these two terms, but okay, reversible processes, when a process occurs, changes in the system happen and changes in the environment happen. Okay, when this coffee gets cold, the coffee has gotten cold and this room gotten slightly warm. Okay? A process is reversible if you can take the environment and the system back to its original state. Okay? So a reversible process is one in which the system and the environment can be returned to their initial conditions. All naturally occurring processes are known to be irreversible. Okay? Heat flows from a hot object to a cold object. That's a natural process. It is not reversible. Heat won't flow from a colder region to a hotter region. And why doesn't it do that?
Delta S must be greater than
Yeah, so if that happened, delta S, entropy of the universe would decrease. Yeah.
What's something that is like reversible?
A frictionless process is reversible. So, if there was no friction.
If you add outside energy to reverse a process, is it still considered irreversible?
Well, so
Not the same process anymore.
no, okay. So this gets cold. I can use a heat engine, heat pump to put heat back in here, except that this room will be warmer than it was before.
Just run the AC.
You'll make it even warmer. Yeah, I mean, you're doing work to. So think of a nice, totally isolated system. You got to bring the universe back to its original state. Okay, so this is just an example. If you pour hot water into a glass and place the glass on the table, the water will slowly cool until it reaches the temperature of its surrounding. This is an irreversible process. You would be astonished if instead the water got warmer and the room cooled down. Yeah? So we need a new physical principle, and that's what we're going to talk about. Okay, again, same thing. All real life thermodynamic processes are irreversible. Okay, so in all processes that occur naturally, entropy is increasing. Change in entropy is greater than zero. Okay? Only in frictionless processes, reversible processes, change in entropy will be zero. Okay? So entropy is the new function, thermodynamic variable we're defining. It's denoted by S. It's a state function. What does that mean?
Outside.
What to say, it doesn't matter what path you take, it matters what state you're in.
Yes, so a point on this diagram is, this gives you your state. Okay, so the entropy value just depends on your state. Okay. Entropy is a measure of the disorder in the system. It's a state function, just like temperature and energy, pressure, volume, and so on. Change in entropy during a process. So let's say something is cooking, and what is the entropy change is your question. So we will be interested in calculating the change in entropy during a process. So we'll show you two ways of calculating change in entropy. Okay. This is the practical way of doing it. We just did it. Okay. Change in entropy of a system is the heat absorbed or given up divided by the temperature at which this heat is given up. Okay. We will very briefly talk about this last one. Okay. And I'll do this at the end of the chapter. This is Mr. Boltzmann. He was a very smart fellow. And look at, this is his tombstone. And on the tombstone, look at that. He was most proud of that. That's the formula for the entropy. That's a constant. We now call it the Boltzmann's constant. Log, natural log of W. What W is number of microstates available to a system for a given macrostate. And so right off the bat, I'll tell you, this is almost impossible to calculate for many systems. Okay? So in fact, you could calculate the absolute value of the entropy if you could calculate this. Very hard problem. Okay? So let me explain what microstates are. Okay, so how many molecules are there in this room?
Something to do
27.
with 27.
I'm sorry?
10 to the 27.
10, very good. And you know, there's lots of empty space here. So I'm just going to give you a sense for what this number is. Okay? So let's break this room into slots. Okay? And you can only put a molecule in one slot. Okay? You see, there's lots of slots, and we're putting molecules here. That's one microstate. And then I'll do another arrangement. That's another microstate. An impossibly large number of microstates. Okay? So if the system went from this initial state to that final state, okay, the initial entropy would be K log Wi. The final entropy would be K log W final, and change in entropy is K log W final. Okay? And that's an impossible, well, I mean, that's a very hard problem to do. So you wouldn't do it unless you really very badly want to do it. Okay.
So how do we realistically use this equation at all? Are we just looking at extremely small?
No, I mean, in research problems you need to. So you start doing research with black holes and stuff like that.
Yeah, the computer could probably do that.
I'm sorry?
The computer could do that.
No. Well,
That's what we want.
Stephen Hawking and all those guys used to use that. Yeah. All right. So we are going to use the first formula, okay? And in practice, for engineering applications, that's all we need. All right, so change in entropy, we'll use this formula, okay? Entropy of a system can be calculated one of two ways. Change in entropy in terms of heat gained or lost and the temperature of the system. In terms of the number of possible microstates for a given macrostate of the system. Now you sort of have a feel for that, okay? But this is a very hard way to calculate it, and we won't be doing that. Okay. The entropy is the system is the natural logarithm of the number of different ways the total energy can be divided up amongst its constituents. So that's another way to think of the microstates. Okay? So S, this is Mr. Boltzmann's baby, and you can think of this as number of different ways the total energy of the system can be divided up amongst its constituents. Okay, so let's say I have $1 million and I give it to you guys. How many different ways can I distribute it? Yeah. I'll give him all $1 million and nothing for you else. Energy is the ability to do work. Okay. Entropy is a measure of how much energy is not available to do work. Okay. So this came about because we realized once we tried to convert heat to work, like you do in your car every day, all the time. When you try to do that, you soon realize that you cannot convert all of heat to work. Okay? And that was a shocking revelation. Okay? So that unavailable energy is of interest in thermodynamics because the field of thermodynamics arose from efforts to convert heat to work, the steam engine and all that stuff. Okay? So entropy is a measure of how much energy you cannot convert to work. So in your car, what's the efficiency of your car?
30%.
Yeah, so you're very optimistic, more close to 20, 25%. Yeah. But you're good. So 70% is not available to convert to work.
Is there a theoretical limit, or is that just,
Well,
is that the theoretical?
So you paid for it today, so we'll talk about it. Okay, you heard of the Carnot engine? Okay. So you'll learn about it in 5 minutes. That'll give you the theoretical limit. All right, so change in entropy is equal to when the system goes from the initial to final state, change in entropy for each small step is given by that. And then you sum up all the changes and you get the total change in entropy. Yep. S final to S initial. Yeah. All right, so we will do a couple of problems where we'll calculate changes in entropy, but we'll show you for a simple case. Okay, here's a thought experiment used. I mean, it's hard to do this experiment, but so here's a thought experiment. We'll talk about this. So what we'll do is we'll take a gas in this chamber, and there's a valve. Here's a vacuum in this chamber. Okay, perfect vacuum, and we will open up this valve, and this gas will expand into this open chamber. So eventually the gas will occupy this much space. So here's the idealization. This is called free expansion. Okay, okay, this is vacuum. Okay. Okay. Now, this gas that is expanding, it's not pushing against anything because this was vacuum. So when this gas is expanding, it's not doing any work. Okay. See, here I did work because I'm working against gravity. I'm applying a force against gravity. There was nothing to push against there. You're not doing any work. If you're not doing any work, are you spending any of your energy? No. If you're not spending any of your energy, is your temperature changing? No. Okay. So in this free expansion, so this is an idealization, but we're using it for illustrative purposes to show you how to do a calculation. Okay, so we'll consider this free expansion. The temperature of the gas will remain the same. Its volume has changed. Okay. So we'll calculate the change in entropy. Temperature, pressure, and volume of a gas fluctuate unpredictably during an irreversible process. Okay. So during this free expansion, the gas has gone from this initial volume to that final volume. Okay. Its temperature didn't change. So you should be able to connect these 2 points with an isotherm. The gas actually didn't go through there. So if you could measure, well, now defining the concept, so I'm going to draw as the gas is leaking, there's the volume. Okay, and if you were to measure the pressure of the system and its volume as a function of volume, it would wildly fluctuate like that. And it wouldn't be the same every time. Next time you do it, it'll go like that. So how do I calculate the entropy? So here is the trick, and I want you to understand this. Okay? Each time you open the valve, you guys understand that the gas is going through this path like that. It's unpredictable. And I want to calculate this change in entropy. Well, this is a state change in entropy is this difference. It's path independent. Whether it goes along this path or along that path, change in entropy would be the same. So what we'll do is we'll calculate it along a path that we're familiar with, an isotherm. Your system actually didn't go through that path, but you calculate the change in entropy along that path, and that's the same entropy change as for your gas. And that's the trick. So this trick is used all the time. Okay? This or similar trick. Did you guys understand that? All right, so that's all. So since entropy is a state function, the integral below can be evaluated along a reversible path. Okay, and this isotherm is a reversible path. Yeah. Even though your system didn't evolve along that path, as long it coincided with the path, the endpoints coincided with this path. So you're going to calculate it along that path. Okay? All right. So during the irreversible free expansion of an ideal gas in an insulated container, so temperature remains constant, and since no work is being done. Okay, you're not pushing against anything. All right, so now we've connected these 2 points by an isotherm. Okay, and now we're not so this free expansion has the same endpoints as this isotherm, and so we're going to calculate the change in entropy for that. Okay, all right. This is the first law of thermodynamics. So a small change in internal energy is equal to a little amount of heat added minus the work done. Okay. Change in entropy is dq by T. Okay. And dq is dW because during an isotherm, internal energy doesn't change. and dq is dw, which is pdv by t. And for an isotherm, P is equal to nRT by V. T is constant, so P is nRT by V, dV by T. So the T cancels, and what you get is I dV by VD, and there is the integral. Okay. So what we have given you is the change in entropy. We've calculated for you the change in entropy during an isothermal expansion, which is also the same for a free expansion. So for one process, we've given you a formula for the change in entropy. Okay? So in an isothermal expansion, where the temperature is constant, okay, we've given you the change in entropy. All right. We'll do it for a more general process. What's a more general process? We're not going to keep temperature constant. Okay. All right, so here's a general process. Here is the first law of thermodynamics again. Okay. What kind of processes does the first law of thermodynamics apply to? Oh, very good. It's a law. It applies to all thermodynamics. Okay. dE is dQ minus dW. So dQ is dE plus dW. dW, the amount of work done, is the pressure at that time times dV. Okay. And of course, pressure is nRT by V. So we're going to substitute that nRT by V dV. Okay. So dQ by T is dE is change in internal energy is N times the molar specific heat at constant volume. That gives you how much energy you've added. Okay. So this is that. And so we'll divide this by T, that by T. So dt by T, nR dV by V. So thus change in entropy is this integral, and when you integrate that, integral of dt by dt is log t, so you get log t final minus t initial, t final over t initial, plus n log v final over v initial. All right. What was this process for? This was?
Isotherms?
Isotherms, when the temperature was constant. Okay, this is for all processes. Okay. For isotherms, the temperature is constant. This would be 1 and this term would be 0, and you get back that expression. Okay. So what is this guy? What do we have here? Change in entropy for any process, but there's one caveat. Your system is an ideal gas system. Okay, that was the assumption. Okay. For any gas. Okay. Okay. So you can change your pressure, volume, whatever the heck it is that you want to change. Okay, you can calculate the change in entropy. Okay, so we saw that the entropy of a system and its surroundings increase during irreversible processes. and remains constant during reversible processes. Okay. So again, in nature, there aren't any reversible process. So for a reversible process, this would be true. Okay. Notice it would never decrease. Okay. You never see. Okay. It never decreases. All right, so what we learned so far is we introduced the concept of entropy, okay, to tell you why certain processes don't happen in nature. That's what we said. Okay? We told you why heat doesn't flow from a colder region to a hotter region. You already knew that, it never does. You were born with that knowledge. We just told you why it doesn't happen. That's all. And why doesn't it happen?
Because delta S must be greater than 0.
Right, so if that happened, then delta S would be less than 0. Okay, so here's another thing you can think about, pretty profound. So you just learned that no process happens where delta entropy decreases, and even in reversible processes, entropy would be constant. So what is happening to the entropy of the universe? Constantly increasing. Okay. So what is the steady state? Where are we headed?
To 0.
To when the entropy of the universe has reached maximum. And that'll happen when the temperature is uniform, and that's called the heat death of the universe. Okay. All right. Heat engines. What are these guys?
Convert thermal to mechanical.
Yep. So they convert heat to work. Okay. Mechanical energy or electrical energy or whatever. Okay. So what is a nuclear power plant? It's a heat engine. What's a coal power plant? It's a heat engine. What's your car? It's a heat engine. Yep. And so on. So heat engines are devices that convert thermal energy to mechanical energy. Okay, so here's a cartoon representation of a heat engine. Okay, we're going to take heat from a reservoir. Okay, so the reservoir is hotter. We're going to absorb heat, and we're going to try our best and convert as much of it as possible to work. And what you cannot convert, you dump out in the environment. Okay, so every time I put $5 of gas, I convert that to $1 of work, motion, and I'm throwing out $4 into the environment. All right, all the heat engines have a working substance which goes through a cycle. In an automobile engine, the working substance is the gasoline-air mixture. Do you guys want to see how the automobile engine works? I mean, this is just a little...
Yes. Sure.
Yes. That was an emphatic yes.
Machines are cool.
What's that?
Machines are cool.
Yeah. All right, so I'll brief. So here's a cylinder. What you'll do is put air. Okay. You'll put air fuel mixture in this cylinder as it is opening up, and then you'll compress the mixture. Why do you compress the mixture?
So when you heat it, it pushes the piston back out.
Pressure increases the temperature, causing it to combust.
Okay, so you put an air fuel mixture. When you compress it, it warms up. and you just want to warm it up enough to below its natural combustion temperature, and then you light it up. Your goal is for all of the gasoline to burn. And even then, in your car, apparently only about 70% of the gasoline burns. So is there anything you can do to make it better?
I'm sure there's a bunch of improvements to be made.
That's what a turbocharger is.
Mm.
It compresses more air, okay, warm air. All right, so the cylinder is going to expand. You're going to put air fuel mixture in, compress it, light it, and now you've generated heat, and that will push it, and that's the working cycle. Okay, so that's what's going on.
I'm Jake O'Neill, creator of Animographs, and this